Hello, this work on machine learning-based navigation has been done by the Spatial AI team of Naver Labs Europe with authors Guillaume Bono, Hervé Poirier, Leonid Antsfeld, Gianluca Monaci, Boris Chidlovskii, and Tristan Wolf. Classical robotics addresses navigation with mapping and planning. Paths are calculated on maps, waypoints are selected, velocities are calculated, and then maintained with low-level controllers. As long as maps are accurate enough, this allows for quick navigation, as we can see in this example. The problem of these map and plan methods is their dependency on accurate reconstructions of obstacles in complex structures, in particular when inputs are single array lidars, as seen in the example. Machine learning-based solutions have the potential to adapt to a large variety of situations and can potentially handle complex scene structures, in particular when trained from visual input. The main hypothesis is the high fidelity of the simulator used for training, and much progress has been made with photorealistic simulators lately. However, these agents are mostly trained in simulation with simplistic or absent motion models. Here we show in red the velocity commands given by a neural agent with discrete updates in time between which velocities are constant. The velocities of the real agent, shown in green, left, will be subject to physics such as inertia and motor forces, which is classically not simulated, as shown in green on the right side. At testing, when deployed on the robot, this absence of learned physics must be compensated and leads to very slow agents, for instance by closed-loop control on positions instead of speeds, stopping the agent after each decision. Alternatives do exist, but always lead to quite slow robot motion as the agent is unable to anticipate complex motion. In this work, we equipped the Habitat simulator with a precise robot motion model identified from real robotics data. The agent learns to correctly anticipate future states, accelerating, braking, turning, etc. Our agent takes RGB and LiDAR scan inputs as well as position estimates from external systems. The agent does not have access to a map. It predicts linear and angular velocities discretized into 28 classes. We test on a Naver Rookie platform which has been equipped with an onboard GPU. All computations are performed on the robot itself. At testing, the end-to-end trained agent takes decisions at 3 Hz, predicting velocity commands which are translated into motor speed set values. The onboard PID controller maintains the corresponding wheel speeds over time. When the neural network takes a new decision, every 300 milliseconds, the velocity commands change instantaneously, shown in red. The physical robot, however, will accelerate and decelerate, turn, etc. It will be subject to physics, and real velocities will evolve slower, shown in green. This is the behavior we want to replicate in simulation. We jointly model the combined package of robot, sensing delays, and control stack together as a single second-order dynamical model. This model runs at 30 Hz, 10 times faster than the agent, and translates actions into realistic agent state updates. This model has a set of parameters which must be fit to the characteristics of the robot and its software stack. To this end, we record a small set of trajectories obtained with the target robot, which was controlled by experts with gamepads. We recorded odometer poses, and from these parameters, we used classical system identification to estimate the parameters of the dynamical model, which was then integrated into the Habitat simulator. Here we see a side-by-side comparison of a real recorded robot trajectory on the right and the dynamical model replayed in simulation on the left, using the same initial condition and the same velocity commands at 3 Hz. The similarities in agent motion are apparent. After training in simulation, we deploy the agent to the robot as is. The agent is capable of navigating quickly 1 meter per second. It is surprisingly robust and capable of avoiding complex obstacles and navigating around small areas with fine structures. It avoids humans and dynamic obstacles, although it has not been trained for this. The majority of the failure cases is linked to long horizon planning and failures, which are inherently more difficult for end-to-end agents without map access. We compare the method with baselines in simulation, including the dynamical model, as well as with the real Naver Rookie robot. Training with constant velocities without dynamical model is not working. The behavior is unexploitable, the agent keeps crashing into its environment. Position-controlled agent is adapted after training by calculating the corresponding velocity commands. Its behavior is acceptable. The fact that rotating and linear motion cannot occur at the same time leads to some success in simulation, but this does not transfer well to the real robot. The agent with the identified motion model achieves near-perfect success rate in simulation. When transferred to the real robot, performance is the best. We compare the method with a ROS2-based planner which uses a 2D occupancy map constructed beforehand. To be comparable, we fine-tuned our agent on a Matterport scan of the sale building. While the ROS2-based planner is still more efficient, it requires many experiments to fine-tune its parameters. Future work will address the visual sim dual gap and that training from real robot data. Thank you for watching.